I need to know what I can get away with when I start talking up here and lying. No, I'm just kidding. As the title of the presentation is, oh, can you throw it up here? Are you still good? Still working on it? I'm going to try to keep this at the basics, right? I do want to try to not go overboard on the technology here and get into too much. But I'm curious, just so I know kind of where to start. Who in here has never used an OGI camera? Not trying to call anybody out. Handful. Okay, good, good. Our booth is, no, I'm just kidding. But yeah, I want to, we good here. Oh, can you just click on this, click anywhere on there? There you go. Awesome. Thank you. All right, yeah, so I want to, before I get into, because there are a handful of people here that may not be as familiar with what optical gas imaging itself is, before I start digging into what quantitative optical gas imaging is, kind of run over the basics of what optical gas imaging is, what it can do for you. Well, this is just, hang on just a second. Well, it's missing a whole lot of text there. Well, optical gas imaging is missing the videos that didn't pull through on the presentation here, so apologize. But optical gas imaging, in theory, maybe pull this up. Don't have the videos. If you haven't seen one, there'll be some throughout here. But in essence, we take a general off-the-shelf infrared camera and we optimize that to be able to see gas. And what we're doing in that regards is we're optimizing it in accordance to how that gas absorbs energy, right? So what's unique about this would be very similar to an everyday infrared camera. Everything inside this actual box, that's a high-end cooled camera. But what's unique to an optical gas imaging camera is this little green box, right? That's the filter. FLIR puts these inside the camera. It maximizes sensitivity of the camera. It ensures that whatever camera you pick up, it will see that gas. We make different little filters for different gases, right? The majority of the ones we talk about here would be hydrocarbons or VOCs. We make one for carbon monoxide, carbon dioxide. We make one for hydrofluorocarbons. We make one for ammonia and sulfur hexafluoride. But in general, that little green sliver right there is what makes an optical gas imaging camera different than a regular infrared camera. And if you look at this, what do we do with this green thing? We utilize it here, right? We're maximizing the ability for the camera to detect emissions by looking at the wavelength, and this is how methane absorbs energy in what's defined as the mid-wave infrared region. So again, had to get through that a little bit, but sometimes it's like, I thought you said you weren't going to be technical and you're showing me graphs of methane, absorption. This is about as basic as I've ever been able to figure, right? An infrared camera receives energy from objects, right? So a lot of the times the videos didn't work, but you can see people, you can see tanks, you can see the ground, you can see clouds, you can see all of the pieces of equipment in here. In this case, just imagine that we've got a processing plant or something in the background. The camera will create that image. Now, what happens at times, the gas will get in between the camera and where that image is. That gas will absorb energy and it will block the capability of the camera to see what's behind it, right? So we're in essence able to see it because it's blocking the energy from behind it. The most general and basic principles of optical gas imaging is that right there, right? We're able to see something because it actually blocks out the capability. It's the same thing as, kind of like smoke, right? Smoke pops up, you can see it, it just blocks everything else out from behind it. We get into the science behind this. There are different types of infrared cameras, and mention that we've got a full portfolio. But if you look at the full electromagnetic spectrum, you've got the visual spectrum down here. In here, you have what's called near infrared. There are some near infrared technologies that are here. Methane does have some absorption in near infrared. It doesn't have as much data on how it affects various gases. The majority of what we do is what's called the mid-wave infrared, mid-wave infrared region. That's where hydrocarbons are in what we call the functional region. What we mean by that is, generally speaking, from that 3.2 to 3.4 wave band, all hydrocarbons, I can't say all, we've only tested like 400, but generally all hydrocarbons would absorb at least some energy in 3.2 to 3.4. right? So that's why it to be the functional. There are different gases that may absorb different areas outside of this, like methane, for an example. This is going to be the 320. Methane has a very unique characteristic because it also has a fingerprint. A lot of gases do. What we mean by that, this is functional, right? They're all together. Fingerprint, they're all different, right? They're separate. Methane, as an example, has a peak absorption around 7.7. Was it ethane? No. Yeah, ethane, I believe, one of the gases out here, has a peak absorption at around 10.8, right? So there's different ones and they're scattered throughout the long wave region. And so that's kind of where we look at this. And as I mentioned, the functional side of hydrocarbons, this is, four of the most predominant gases that you would see in a general oil and gas type of various applications, from your upstream type of stuff to more of your mid or downstream stuff like a benzene. You have a functional grouping of where they would absorb. They're not all exactly the same. You'll notice that they have various breaks, but from 3.2 to 3.4 microns, they're all going to have some sort of absorption in that region. And I have lines. Again, so how do you tune it? We talked a little bit about this, and this is what is unique. Our cameras are, these mid-wave cameras generally are what we define as cold, right? They're cooled cameras. So we have you'll hear them running. You'll hear that running behind you. I call it the sound of money because I work for FLIR. But generally speaking, we have a cooler built into this, and the camera has to be down to often like 77 Kelvin in temperature, the detector does, to be able to work and produce an image. So qOGI, I want to get into a little bit of the technology, the fundamentals outside of the basics of optical gas imaging. I want to talk about why it works, the qOGI triangle, as we call it for FLIR. The tips and tricks of using qOGI and some of the what I call it the lookout fors, right? The things to consider when you're doing this in real life. And then we have done some validation studies through either ourselves or Providence Photonics, who is our, we have a partnership with them as a minority share investment company with Providence Photonics, and they're the organization that develops our analytics for our quantification solution. So if you look at this, we're going to go in detail over this. No, I'm just kidding right here. The difference between this definition and the other one is very simple, is we're able to quantify. And the quantification happens, and I'm not going to break down, if this were the advanced quantitative optical gas imaging that the Providence team puts on, they actually break down what each one of these symbols do. Just basically putting the delta intensity, that's the readout, the intensity of quantification, the intensity of the gas. That is your quantification reading, and this equation is how it's actually made. Or basically put, there's three ways to do qOGI, right? That within the FLIR technology, and I will make the disclaimer that when I talk about qOGI technology, I don't want to mislabel another manufacturer, so I'm going to speak in terms of what FLIR does as it relates to a quantitative optical gas imaging. The three ways are going to be tethered, and what that is, that's the most advanced way that we can get the best readings. You're taking a hard data stream out of the camera and you're plugging it into a specified engineered tablet, which is a computer, right? Believe it or not, that big tablets that you get, we can't put the processing power inside of the cameras that fits the processing power of an entire computer. And so that's why you're always going to get a little bit better. And this works with all GF and G series cameras being able to plug this. The G series, we've got a update that's coming out this month in which the tablets will work with the new G series camera. The other one is the Q mode feature. And what that means is when we had cameras, when we first came out with a partnership with Providence, and we had the FLIR modeled quantitative, we also had an ATEX camera. And the only way to do this is you connect the camera to the tablet. And we said, hang on, you can't do that in an ATEX area or location. And so what we did is we put in the camera a very basic way to just store a file. And you can post-process that file in the tablet after the fact. The newest one is what we call quantification in camera. Now, the new G series camera that we have on the tripod out in the foyer where our booth is, now all of that is gone away. The tablet's gone away. You do still need to use a tripod because we're analyzing pixels, minute size pixels moving over spatial and temporal, regions, right? So, but we have the capability of quantification in the camera. Now you set it up and you hit go and you wait 20 seconds and it gives you a file and the capabilities to just go quantify the next emission that you see. The history, the evolution of this, it's not it's not a quote unquote new technology, but it's not all that old. The very first quantitative optical gas imaging solution was brought to the market by Providence Photonics before we were partnering with them, but not in formal capacity, called the QL100 in 2016. And if you think about that, that's still a pretty new technology in the grand scheme of things. You start looking at various technologies that are utilized in the oil and gas industry. When I started this role, I worked with Providence a little bit deeper and began to integrate a more consistent user experience, and that's where the Providence QL. And then when we did enter to a formal partnership with them, we actually have the FLIR branded QL320, which has gone through a different revisions or different versions. That is the current quantification model for the secondary piece for the tablet type of modeling. The big difference now is you don't necessarily is there an advantage to buying an additional quantification tablet? Yes, it does have some additional features, right? The best quantification that you're going to get, and we'll talk about that in some of the validation studies, more data is better, right? So if I can hook it up and get a longer memory, a longer measurement cycle than like a minute or longer, or have it just running, you're going to get a little bit better data. And that's just happens to be. It's very challenging to quantify a turbulent gas leak that's always changing, right? If you've ever looked at an OGI video, it's not a direct stream that looks like a hardened rectangle coming out of a leak, right? It's completely and always changing with respect to dynamic natures of gas. Some of the advantages, again, streamline, super streamlined, same analytics. The analytics package that's built into the camera is slightly streamlined. And of course, for the continuous type of stuff, we can't do that. Again, all it does is after you run it, it just drops you an IR image. And on the top left of that image, you've actually got your quantification number, and you can move on to the next one. I'll give you a quick summary of what it looks like, and then walk away from it. And then the potential to meet regulatory demand, we've made comments to the EPA on Subpart W on various things to be able to potentially utilize the quantification technologies that we have to meet regulatory demand that's out there for quantification of emissions outside of just detection. As we talk about quantification, and really OGI in general, but this triangle was kind of brought to us with the Providence folks, is you start looking at what's needed to either just see a gas with an OGI camera, in particular, for sure, to be able to effectively quantify that. The things that are needed, very simple, right? You're going to need the G is the easiest. Gas has to be present. Believe it or not, if there's no gas present, we can't quantify that. Pretty hard to do that. So the second one is that little filter we talked about. The camera, the IR absorption peak of the camera has to match the IR absorption peak, or the filter of the camera has to match the IR absorption peak of the gas, right? Very simple to be able to do that. Right now, we only have quantification capabilities in the hydrocarbon realm. We're looking at whether we want to expand that into some other different type of compounds. But one of the keys that isn't talked about as much, realistically, was never talked about in my early days at FLIR and OGI world, was how delta T affects optical gas imaging, and it was really brought into fold as we began to talk about the quantitative optical gas imaging side of things. So as we look at the theoretical calculations, again, I'm not going to get too much into all of this stuff. I thought that was hidden, but the gas, right? Is there gas present? Very simple. How much gas is present? And then we began to work on that. And so this is just two direct leaks, propane at 2 liters per minute propane at 6. That is just the quantity of gas presence, and that's the amount of that. You can see that there's gas present. Very simple. General rule of thumb, and I may talk about this later as I talk about tips and tricks. If you can't see the leak in normal mode, you're probably not going to be able to quantify that, right? The quantification is not to the point, or it's not ready to be able to quantify the smallest and smallest of leaks. It's not the intent of that at this time. And we're working on it, but that's usually the rule of thumb. Which leak is bigger? Curious, left or right? Anybody? That kept everybody asleep? Left leak is bigger. Well, one's propane and one's methane. They're actually the exact same size. So when I talk about the absorption of this, we also talk about the coefficient, which is also commonly referred to as a response factor. Nobody have ever heard of that until Appendix K came out, and everybody says, what the heck's a response factor? A lot of that was based off of this research by the Providence Photonics team. And in essence, if you look, methane with using a cooled optical gas imaging camera, methane has a response factor of about 1/3 of propane. That's why the leak looks a lot lighter. But in reality, those are the exact same size leaks coming out of there. One just looks lighter because it's not as strong of a gas in the filtered region of the camera. And the last is delta T, right? What happened? Where did the leak go? Pretty common. Now, if those of you can see from this type of thing, you can probably look and see it over this chain link fence. This is just a scenario. This is a wall, an exterior wall that was hot still from the evening. And this is the background after the sun went down for a while. Chain link fence still has a little bit of heat. But what's happening here is that you've lost the delta T. In this case, there's a lot of delta T between the background and the ambient air, which is assumed to be the gas temperature. In which case, on the right, there is very minimal delta T from just the background, which is the ambient air, compared to the gas temperature, which is the ambient air, right? But you may not be able to see it in this, but if you look closely, you can see it crossing the chain link fence. What is delta T, right? Very simply put, if we go back to my previous one, this background temperature, and again, even according to the EPA, if you look at Appendix K, they define delta T. It's assumed to be the ambient air temperature. There's Boyle's law, which comes out related to that, and it just pretty much says that as a gas enters a different environment, it will take the shape thermally of that new environment, right? So have that. The other thing you do need to be aware of with this is there's two different types of plumes. And now I'm going to call myself a liar here a minute ago, right? We talked about gases, and you can see it because you can't see it because it blocks energy, and gases don't emit energy. Not exactly the case, right? Most of the time, 95% of the time, when you see a gas leak, and this is assuming that the camera is set with a white hot palette. Most of the time when you do this, the gas is going to come out. It's going to be black. It's also known as an absorptive plume. What that means is that gas is absorbing energy and stopping the camera from seeing what's behind it. But there may be times in which, I think it's a little hard to see here, but this is white. And this is what's called an emissive plume. That just means that the background energy, like the sky, which is by definition absolute zero, atmospheric conditions change that, but by definition it's absolute zero. The sky is going to be colder than the background, so the actual gas is emitting energy, and we're seeing it because of the energy it is emitting. The first QL 100 that they put out, they said, Mr. Operator, tell me whether you have an absorptive plume and an emissive plume. And I probably got a call from everybody that ever touched a QL and said, what's an absorptive versus emitted plume? So what we did is we changed it. Is the plume color black or white? So all you got to do is put it in, right? What color do you see the gas emission plume? Tips and tricks. These are things that in talking to customers, make sure I think I have plenty of time here, talking to customers, talking to people that use the camera, what did they say were the main things that they saw or either challenges or that maybe we need to educate a little bit more related to utilization of quantitative optical gas imaging? The number one is you can't afford objects. a lot of times, if you think about this, what are we doing? Like, we are looking at a gas leak as it moves from pixel to pixel. And if you think about that, the GX320 has 77,000 pixels in it. And as this moves from pixel to pixel, that's what we're measuring. And most of the time when we do a point emission, we're measuring as it moves from inside of a circle to the outside of a circle. So if you have an LDAR tag, if you have a ribbon that you're doing this, a ribbon floating in the wind looks a whole lot like a gas leak, right? A little orange ribbon floating in the wind. So make sure that when you're utilizing the quantitative optical gas imaging, you don't have a type of thing. So you'll notice this is actually the actual video, and you'll see how much leak there is. It thinks that there's this big rectangle of emissions inside that moves from the inside to the outside and then back in and then back out. And somebody took this and said, man, your quantitative solution sucks. And it gives me really, really high, like 1 million times higher than what we expected it to be. Well, yeah, we fully fully estimate that. So some education pieces maybe on our side was to, make sure and utilizing the technology that you remove any foreign objects, in particular, anything that may cross a boundary, may cross this blue boundary line that we have. The other one is stability is a must, right? So utilizing the technology, you'll be surprised if you've got 77,000 pixels and how small a single pixel is when you're using the camera, right? From, let's say, 10 feet away, we're talking, fractions of an inch. And so I've had multiple customers, and one guy said, Craig, I got a really good video, and I know I was standing really still. I'm like, but you're a considerable distance away, and any little bitty movement, that pixel might be moving a foot at the distance that they were using the technology here. So now it's trying to measure the tops of this building, because that all it sees is a change in temperature, and it thinks, all right, well, that's got to be gas because you told me you're on a tripod, and any pixel movement, change in pixel movement, is going to affect that. So the tripod, the stability is a must. We talked a little bit about the delta T aspect. It does matter. Again, we're bringing radiometric data to get the most optimal temperature quantification, or most optimal quantification reading. So we're taking an individual, every pixel level, we're taking into account what we tell it the ambient temperature is. And we're also taking at an individual pixel level the different temperatures of every single pixel, and that as it crosses that boundary, right? So if I look at something like this, and this is, I don't know if this is a video, but this was taken out at METech. We did our due diligence testing like everybody out at METech, which is great in some aspects. But in this scenario, the actual reading was 32 liters per minute, and that was the actual reading from the METech staff, right, in our blind testing, and they gave us a reading after. We actually did the correct delta T, and I was curious, what happens if I just change the delta T by 2 degrees, right? I just want to move it by 2 degrees off center of where I think it should be. What's going to happen to the reading? And we're at 45. Now, again, not a huge change. You move it by 3 or 4, it gets worse. But if you look at percentages, it starts to actually show that the delta T does matter. And you're doing, now we're off by almost, 40% up. Oh, and there is a video. Didn't know that. So this was this actual leak out at METech, just kind of showing exactly what's happening related to that. The other one is center of the leak. Ideally, most of the time, there's 2 different types of ways to quantify, or 2 different types of leaks right now. I think we're looking at adding a third one for tank emissions, like over the edge tank emissions that Providence has been working with the EPA to get certified for tank emission calculations. So there's 2 different ways to do this, but one of them is called point source, right? It's in essence, what it does is it starts at the center of a leak and it moves out to the edge, like the video I just showed you. And when I talk about that, the other one is called diffuse leak. And what that means is generally a point leak is a pipe that's, I believe, 2-3 inches or smaller in diameter, and that starts in the middle of somewhere and moves out. A diffuse leak is either a very large pipe, so it's a different calibration curve, or it's a leak that may move from the outside in to the inside out, right? As an example, maybe it's trying to measure a leak from a thief hatch, right? The seal on a thief hatch. That might be more of a diffuse leak than a point leak because it's not coming from a single point or from a compressor. The parameter accuracy, as I mentioned, this is what the screen looks like on the QL320. These are the parameters. These are put in for the generally by the operator. We simplified it, right? What color do you see, black or white? Hopefully people can figure that one out. You need to tell it what type, leak type, right? Point or diffused, as we mentioned. The lens will automatically be pulled from the camera. How far away you are from the leak. What is your estimated temperature? I just showed you, the delta T piece, right? Inputting the correct temperature parameter can have an effect. The composition. Now, this is unique, right? What we do is we pull a composition reading from, a single, let me say, our quantification reading is assumed as a single composition. So our single component within a composition or gas. What we say is put the gas that has the most predominant, that has the highest composition percentage within the stream. We do have spreadsheets that you can utilize after the fact. So if I ran this and methane was the predominant gas in the stream, right? And it gave me a number of 100 liters per minute, but methane was only 60 and propane was 40. I showed you earlier, right? Methane is more, the video was fainter of the leak. And so you can put this into a calculation spreadsheet after the fact to get a truly accurate reading. But keeping in mind that you are measuring the other gases, you're just measuring it with the assumed response factor that was for the first gas. Some response factors don't matter much. If I went back to that, propane and butane and ethane are almost all the same. Methane is much lower. Benzene is kind of in between. So you do have to put what composition you have. And then the wind speed is it's important, but there's only 3 characteristics: calm, normal, and high, right? 0 to 1, 2 to 10, over 10. And so very, very, a little bit more basic. The effects of wind, just like optical gas imaging, you do want to ensure that the emission is moving to the side, right? Emission moving directly away or from me. Again, we're utilizing 2-dimensional technology to measure 3-dimensional leaks. It can't measure the 3-dimensional leak as it's on a Z factor pulling to me. So utilizing the qOGI technology, you want to do everything that you can when you see the leak and start to measure it to make sure that leak is moving off to the side. And then the limitations and what you have, we talked about delta T. We want to try to keep that delta T at 2 degrees, right? Optical gas imaging, while I disagree with some of the Appendix K statements that it needs to be 2 degrees or 5 degrees in insurance, if you put a camera in high sensitivity mode, delta T very rarely matters, right? If it's minimal. But again, as I mentioned, if you use HSM as the only way you can see the leak, it's not for qOGI. So with qOGI, you do need to have a minimal delta T of around 2 degrees C. There are different limitations in how far you can see. In the current calibration curves we have, the general lens is from 5 feet to 54 feet. We can go up to 90 and 210 feet, depending upon the lens configuration you have on your camera. And then a common question I get, what's the max and the min? We're updating this now. We hope to have a release sometime soon, right? We've got the point release that goes up to 40 standard liters per minute. We go up to 300. That's 12 kilograms an hour of methane for the diffused release, for a larger scale release type of stuff. Usually a pinhole release doesn't get to 12 kilograms per hour, or you can hear it from a mile away. And then understanding clouds. Clouds are not a friend to quantitative optical gas imaging, right? Utilizing clouds. Slow-moving clouds look a lot like slow-moving gas. They are dynamic in nature. They're consistently changing. So making sure you understand the clouds and what you have, even with the capabilities to do the masking features that are built into the technology, it's going to be very challenging to get that. When we talk about polarity and choosing white versus black, in the polarity that you would have. This is the actual leak, right? 60 liters per minute. We chose the correct white plume. And what we mean by this, you can't see this leak is pushing out this way. So what's happening here is the leak's going from here over the parameter, and none of this, the only thing that is eliminated from the equation is what's in red. It's our delta T check. But Craig was too stupid and did it in black plume whenever it really was a white plume. And I realized that, and this is what it looked like. And I was wondering, man, I can't get a reading anywhere. It's 4 liters per minute versus actual of 60. That's because it's only catching this much of the leak. It's not getting out to the edge because it's ignoring the majority of what you have there. And it's only catching where it's not red. So ensuring your polarity is correct. Oh, these do have videos. And then we can do the same thing. We start looking on this type of leak in the inverse, right? This is one that is black plume, but you would want to, accidentally choose white. What happens? 16 liters, 3.6 liters, and then 18 liters here utilizing the correct plume. What's the red? This is the delta T built-in feature of the camera. You tell it, hey, I want to know a 2 degree. I want to ensure that I have a 2 degree delta T, and I put in my ambient air temperature. Every pixel that's red does not have the sufficient delta T that you need to do that. And you can see where a lot of that gets blocked off as you're trying to measure that. So some validation studies that have been done with Quantitative. There's some other new ones out that I just found out here recently, but some of the ones that are a little bit highlighted for qOGI. One is a 2015 study that our partners at Providence did in Europe. This was the beginning of the technology to kind of say, is this worth continual investment? And what they did is they directly compared this to a sniffer, right? How can we quantify, how accurate can we quantify compared to a toxic vapor analyzer, TVA, or sniffer? This is just the gases, mixture of 3 each, these, and there's a paper on this out. How did it do? Keeping in mind that these are directed sniffer readings. What I mean by that, this isn't a sniffer going around like a sniffer does, right? I'm blind, I'm checking equipment, I don't know. We're telling it it's that valve. Go find it, right? So the first point of using an OGI camera versus a sniffer has already been taken out because we're telling the sniffer where to go. But now, just for the quantitative, if you look at the average, right? Our average number, our average result was around, it was 6% in accuracy. The average for the sniffer was 31%. So we were about 5 times more accurate. Now, I'm not going to sit here and say that 6% is the individual reading average of every time you use the camera. It will be greater than or less than 6% or 12% or 20%, whatever that number is. But on the average, I think that this was around 100 readings, 100 tests. We performed very well compared to a sniffer. So then we decided, all right, let's go next. And we had a group and an organization out of, at the time, Harrisburg University. Many of you may have heard of Arvind Ravikumar. Scheduled a testing up in Alberta. And the goal of this was twofold. One, they evaluated a lot of technology, but they wanted to also evaluate how they could use technology to quantify remotely, right? That's the huge advantage of qOGI. I don't have to touch this to quantify this. I can quantify that light. As long as it's leaking and I have a camera and a tripod, that's not a problem, right? DTMs are not a problem to quantify with this. So they wanted to figure out how they could do this. This was the result. Not to get in this, what I'll do is I'll summarize a lot of this. The result was we miss high, we miss low. Dynamic gas movement, right? And it's always changing. And what the result of the testing was that qOGI as a technology is going to have trouble on an individual reading meeting a standard deviation number, right? We're going to have a bit challenge to say we're always accurate between this. But the more aggregate data that you get, the more data that you get over whether it's that day, whether it's that site, whether it's your region, whether it's a month, whatever that is, the more aggregate data you get, that number, the more accurate your solution or your resolution is going to be. So if you look at the numbers here, they compared us to at the time a high flow. Now, the high flow is limited. High flows can't measure anything as far as size-wise. So high flow is very limited, but the high flow was 10% in standard deviation in percentage of error. qOGI was 18%. And the people that we've talked to said, I'll take it, right? That's awesome. Individually, we may be high and low, but the more aggregate of the data that you put in, we actually have that. So what did we do? We said, all right, I like the results. Let's do it on our own. Right? Let's go out and go to METech and rent it for a week and go test the technologies. And while we're there, let's figure out whether this theory of aggregate data measurements for qOGI is accurate. So we went out there and we did about 90 data sets of evaluation for qOGI while we're evaluating some other technology. These were actual leaks. These were monitored by the METech staff. They're the ones providing the numbers of how much the leaks were on an individual data set basis. And I'm not as good as Arvin, but this is my graph of this. And you'll notice a very, very similar plot, right? We've got high, we've got low. Our percentage of error was 4%. And this is excluding some cloud samplers. We did, and again, full transparency, those videos that you saw a minute ago with the clouds and it's all red and you can't do anything. We took those knowing that the reading's going to be crap because the clouds are in the background. So if I remove just those, which we still had an 80 sample set, our average error according to the METech blind testing was 4% on this. This was their actual summarize. This is their total was 3,151 liters per minute. Ours was 3,281. So on an aggregate setting, we're pretty comfortable in this. On an individual setting, you will have this. The other problem bias is individual high. Individual low, if you just get 0 every time, you can't go any lower. But if you get high every time, the numbers do start adding up. This was the data set, right? We were off. We knew we would be off when we took these readings. We were off by from 450% to 4,000% utilizing this. I say this for 2 reasons. One, be careful, right? If there's clouds that are slow moving in the background, the technology does look a lot like gas, and it can be a little bit challenging to do that. And that's what I have. I don't know how, I've got 5 minutes. If anybody has any questions, more than willing to answer or let you guys be. Anything? Awesome. Yes.
Is there an option to add multiple gases? And is there an option for mixture of gases within the drop down?
No, right now we've got 8, I think it's 8 predominant gases. Love to hear feedback of whether the problem is the gases usually change in your stream. A lot of people, guesstimate, but may not know exact, right? It changes every day, every minute, whatever's happening in your process, that's going to change. I know downstream they have a little bit better control of the composition of where they know they could be. We've talked with the Providence engineer. I don't think it's out of the realm of an option to be able to say, all right, we'll give you maybe 2 users, maybe it's 4 users, and you put your own composition. We can easily adjust the algorithm to not be 100% this gas, to be 20, 20, 20, 20, and 20 of various response factors. The challenge that we've seen is that most of the time, those gas, they don't know exactly what it is until they run a composition report after the fact. They may get a general guess, and that could maybe be better than what we'd have. But it's not in there today, but it's not out of the question. Thank you for your time. We'll be back in here in an hour for the optical gas imaging and regulation panel with a couple of operators and Ned from the EPA.